Hello and welcome to this quiet corner of the universe. Please make yourselves comfortable. Today we're going to embark on a journey through space and time. We've all heard the forecasts about a grand cosmic event awaiting us in approximately 4.5 billion years, the collision of our galaxy, the Milky Way, with its closest neighbor, the Andromeda galaxy. This event seems so distant, almost mythical. But what if I told you that this galactic collision has already begun, that these two gigantic spiral galaxies are already touching right this very moment, even as you listen to my voice? In this sleep lecture, we will dive deep into the invisible realm of dark matter, into the vast gas clouds surrounding the galaxies, and discover how our cosmic homes are connected on a level we are only just beginning to comprehend. Get ready. Our journey to the true boundaries of the galaxies begins now. To grasp the sheer magnitude of what is happening, let's first map out our cosmic neighborhood. We do not exist in isolation. The Milky Way is part of a small yet intimate cluster of galaxies that astronomers call the local group. It contains over 50 galaxies, but most are dwarf, faint satellites orbiting two true giants. These giants are us, the Milky Way, and our magnificent neighbor, the Andromeda galaxy, also known as Messier 31. Andromeda is slightly more massive and holds roughly 1 trillion stars, while the Milky Way is estimated to contain between 200 and 400 billion. The distance between us appears colossal, approximately 2.5 million light-years. The light leaving Andromeda takes 2.5 million years to reach Earth. This means we are viewing the galaxy as it was deep in the past, around the time the earliest ancestors of humans were first emerging on our planet. These two titans dominate the local group, and their mutual gravitational pull dictates the fate of our entire galactic neighborhood. Let's begin with what we can actually see. Picture the Milky Way. We are currently nestled deep inside it, residing in one of its spiral arms, roughly 26,000 light-years away from the galactic core. From our perspective, it appears as a hazy band of light stretching across the night sky. This luminescence is the combined light of billions of distant stars within our galactic disk, merging into one continuous glow. The diameter of this massive, visible disk spans about 100,000 light-years. It is a vast, churning place, teeming with life and activity. Stars are born here and eventually die, planets are formed, and at the very center, hidden from view, lurks the supermassive black hole, Sagittarius, a star whose mass is 4 million times greater than that of our Sun. Our galaxy is a complex, dynamic system defined by a central bar structure made of older stars and several bright spiral arms filled with young, hot, blue light. This is our home, our cosmic cradle, and this home is currently hurtling through space, engaged in a slow, inevitable dance with another, even more magnificent cosmic island. This gravitational ballet has been ongoing for billions of years, and its dramatic culmination is already predetermined by the laws of physics. Now let's shift our focus to our closest major neighbor, the Andromeda galaxy. If you ever find yourself under truly dark skies, far away from the glare of city lights, you can actually spot it with your naked eye. It appears as a small, faint, fuzzy patch within the constellation Andromeda. But that appearance is highly misleading. It is, in fact, the most distant object visible to the human eye without optical aid. In reality, Andromeda is a true giant. Its visible disk stretches 220,000 light-years across, making it more than twice the diameter of the Milky Way. When viewed through a telescope, we see a breathtaking scene, a brilliant core, tightly wound spiral arms, and dark, intricate dust lanes. It looks very much like our own galaxy, only bigger and perhaps older. Andromeda also harbors a supermassive black hole at its center, one that is considerably more massive than the one in the Milky Way. Like the Milky Way, Andromeda is surrounded by a massive swarm of hundreds of globular clusters and dozens of dwarf satellite galaxies. For centuries, humans stared up at that fuzzy patch, completely unaware of its true nature. It wasn't until the 1920s that astronomer Edwin Hubble definitively proved that Andromeda was not merely a nebula within the Milky Way, but a separate, self-contained island universe located at an unimaginable distance. This single moment forever changed our understanding of the true scale of the cosmos. 2.5 million light-years. Let's try to truly grasp that number. A light-year is the distance light covers in 1 year, traveling at almost 300,000 kilometers per second. That translates to roughly 9.5 trillion kilometers. Now, multiply that distance by 2.5 million. The distance to Andromeda is so vast that it truly stretches the limits of human comprehension. Even if we could travel at the speed of our fastest man-made spacecraft, Voyager 1, it would take us tens of billions of years to reach Andromeda. That is longer than the entire age of the universe itself. The space between galaxies is an almost perfect vacuum. The density of matter found there is millions of times lower than in the highest vacuum we can create in laboratories on Earth. It is a world ruled by darkness, cold, and gravity. And it is gravity, this invisible force acting over colossal distances, that is the chief architect of the coming cosmic drama. Despite the immense void separating them, this force is slowly but inexorably pulling these two galactic giants together. So, how exactly did we figure out that Andromeda is heading right for us, instead of moving away like most other galaxies? The answer came thanks to a phenomenon known as the Doppler effect. You actually encounter this phenomenon every single day. Think about an ambulance driving past you. The pitch of its siren changes dramatically. It gets higher as the vehicle approaches and immediately drops lower as it moves away. The exact same principle applies to light. If a light source is moving toward us, the length of its waves essentially compresses or shortens, shifting the light toward the blue end of the spectrum. We call this a blue shift. Conversely, if the source is moving away, the waves stretch out and the light shifts toward the red end of the spectrum. That's a redshift. Back in the early 20th century, astronomer Vesto Slipher was studying the light spectrum coming from Andromeda and discovered something astonishing. Unlike the vast majority of nebulae he had examined, the light from Andromeda was noticeably blue-shifted. This could mean only one thing: it was moving directly toward us. Later measurements refined this collision course, pinpointing the speed of approach at about 110 kilometers per second. That works out to roughly 400,000 kilometers per hour. At that astonishing speed, you could reach the Moon in less than an hour. But given the immense distance, this cosmic journey will still take billions of years to complete. By determining Andromeda's distance and its rate of approach, astronomers were able to calculate the approximate date of the monumental collision. The most precise calculations, relying on years of data from the Hubble Space Telescope, which tracked the motion of stars within Andromeda, predict that the initial close pass, the true start of the merger, will occur in roughly 4.5 billion years. What does this mean in the grand scale of the cosmos? Our Sun will still be around then, but it will have become dramatically brighter and hotter well into its phase as a red giant. Life on Earth, assuming it hasn't already vanished, will be utterly impossible. However, the planet itself will likely survive the initial encounter. When considering the universe, which is nearly 14 billion years old, 4.5 billion years is a significant period, yet far from infinite. This is a future that astronomers can predict with a high degree of confidence. This destiny is already written in the movements of stars and galaxies, governed by the fundamental laws of nature. The ultimate fate of the Milky Way and Andromeda is to merge completely, forming a single, even more colossal galaxy. What exactly happens during this galactic merger? Many people picture an apocalyptic scene, stars slamming into each other, planets getting ripped from their orbits, and total chaos and destruction reigning supreme. But in reality, the process will be far more graceful and quiet. The main thing to remember is this: even though each galaxy contains hundreds of billions of stars, the distances between them are immense. If you imagine our Sun was the size of an orange, Proxima Centauri, the nearest star, would be another orange located more than 2,000 kilometers away. Galaxies are mostly empty space. So, when the Milky Way and Andromeda collide, the chances of two individual stars directly hitting each other are infinitesimally small. Instead, the galaxies will pass right through each other like two ghosts. However, their gravity will have a colossal impact. It will warp their spiral structures, drawing out long streams of stars known as tidal tails. The galaxies will complete several of these passes, losing energy and drawing closer with each iteration. The massive clouds of gas and dust within both galaxies will crash together, compress and trigger a tremendous burst of star formation. For hundreds of millions of years, the future sky will be alight with billions of new, young stars. Finally, in about 7 billion years, the cores of the two galaxies will merge. In place of the two spiral beauties, a new, gigantic elliptical galaxy will be born, one that astronomers have already jokingly nicknamed Milky-Way. However, this visible picture is only the tip of the iceberg. In the mid-20th century, astronomers studying spiral galaxies stumbled upon a profound mystery. According to Newtonian laws, stars on the outskirts of a galactic disk should orbit slower than the stars closer to the center, where the bulk of the observable mass is concentrated. Just like in our own solar system, distant planets, such as Neptune, move along their orbits much slower than Mercury, which is close to the Sun. However, observations revealed a completely different picture. Astronomer Vera Rubin, meticulously measuring the rotational velocities of stars in the Andromeda Galaxy and other spirals, discovered that stars on the outskirts moved at virtually the same speed as those near the core. The resulting galactic rotation curve was flat. This was entirely inexplicable by known physics. For these outer stars not to be flung into intergalactic space at such high speeds, they had to be held in place by an enormous, unseen mass generating substantial extra gravity, a mass that stretched far beyond the confines of the visible galactic disk. This was the first compelling evidence for the existence of something we now call dark matter. So, what exactly is this mysterious dark matter? The short answer is, we don't know, but we do know what it isn't. It's certainly not ordinary matter, not stars, planets, gas, or dust, because it doesn't emit, absorb, or reflect any light. It is completely transparent, utterly invisible to all our telescopes. We also know it's not made up of protons, neutrons, and electrons, the fundamental particles that form everything visible in the cosmos. Its nature remains one of the greatest mysteries in modern physics. Scientists hypothesize that dark matter might be composed of some exotic, yet-to-be-discovered elementary particles that interact only very feebly with ordinary matter. The only way dark matter reveals itself is through gravity, and there must be an enormous amount of it. According to current estimates, ordinary, visible matter accounts for only about 5% of all the mass and energy in the universe. Another 27% is dark matter, The remaining 68% is the even more puzzling dark energy responsible for the universe's accelerated expansion. This means the galaxies we observe are merely tiny, glowing specks embedded within the gigantic, invisible structures formed by dark matter. The evidence for dark matter doesn't just rely on galaxy rotation. Gravitational lensing provides another powerful line of evidence. According to Einstein's theory of general relativity, massive objects warp space-time around them. Light passing near such an object is forced to follow this curved path, much like a beam of light refracting through a physical lens. Astronomers observe this effect constantly. When light from a very distant galaxy passes by a closer cluster of galaxies, the image of the distant galaxy becomes distorted. It can be stretched into long arcs or even appear in multiple spots simultaneously. By measuring the degree of this distortion, scientists can calculate the total mass of the lens, the galaxy cluster. And the result is consistently the same. The mass calculated using gravitational lensing is several times greater than the mass of all the visible matter, meaning all the stars, gas, and dust within that cluster. This excess mass is dark matter. The bullet cluster, the result of two galaxy clusters colliding, is the most visually striking example of this. Observations show that during the collision, the hot gas, which is ordinary matter, slowed down and concentrated near the center. Meanwhile, the bulk of the mass, the dark matter, which interacts only via gravity, passed straight through without slowing down and is now located far off to the sides. This provides direct proof that dark matter exists and behaves fundamentally differently from normal matter. This invisible dark matter forms a giant spherical structure known as a halo surrounding every galaxy. The dark matter halo is essentially the gravitational scaffold, the framework upon and within which the galaxy initially formed and subsequently grew. To visualize this, imagine a galaxy not as a flat disk but as an iceberg. The visible components, the stars, gas, and dust, are just the small tip sticking out above the water. Hidden beneath the surface is a massive, invisible chunk of ice, the dark matter halo, which may outweigh the visible portion by 10 or even 20 times. It is this halo, through its immense gravity, that keeps the stars moving rapidly in their orbits. It determines the overall mass and true physical extent of the galaxy. The actual boundary of the galaxy isn't the edge of its stellar disk. It's the edge of its dark matter halo. And these halos stretch into space across unimaginable distances, vastly farther than the most remote stars belonging to the galaxy. Understanding this fundamental structure is the key to unlocking the mystery of the impending collision between the Milky Way and Andromeda. But what else is contained within this gigantic halo besides dark matter? It's not entirely empty. It also contains normal matter. It's just incredibly diffuse and difficult to detect. For starters, the halo is home to the galaxy's oldest stars, organized into hundreds of globular clusters. These ancient relics from the galaxy's formative years orbit the center along highly elongated and chaotic paths. Secondly, the halo is filled with an extremely diffuse and searingly hot gas, with temperatures reaching millions of degrees. Now, this gas is known as the circumgalactic medium, or CGM. It consists of material left over from the galaxy's formation, as well as matter ejected from the galactic disk by supernova explosions. This hot gas acts as the galaxy's atmosphere. It's invisible in the optical range, but it can be detected using X-ray and ultraviolet light. The total mass of this gas may actually be comparable to the mass of all the stars in the galaxy combined. So, a complete picture of a galaxy includes the bright, dense disk and central bulge, surrounded by a vast, almost invisible sphere made up of dark matter, diffuse hot gas, and ancient stars. Just how big is the Milky Way's halo? Until recently, the true extent of its size was unknown, But recent research based on cosmic telescope data and sophisticated computer modeling has finally allowed us to map out its boundaries. It turns out the Milky Way's halo stretches out roughly 1 million light-years from the galactic center. Let me emphasize that, 1 million light-years. That's 10 times wider than the diameter of the visible disk itself. If our halo were visible, it would occupy an area in the night sky hundreds of times larger than the full moon. We are living deep inside this colossal, invisible bubble. Our closest satellite galaxies, the Large and Small Magellanic Clouds, are located far inside our halo and are gradually being absorbed by the Milky Way. This figure, 1 million light-years, is absolutely crucial. Recall the distance to Andromeda, 2.5 million light-years. If our halo stretches for 1 million light-years in one direction, then it already covers almost half the journey to our nearest galactic neighbor. This brings us to the ultimate question: just how big is the Andromeda Galaxy's own halo? Finding the answer to this question was the true breakthrough in our understanding of the impending galactic merger. Pinpointing the true size of another galaxy's invisible halo is an incredibly complex task. We can't send a probe there, nor can we measure the rotational speeds of its outermost objects because they are either non-existent or simply too dim to observe. A different, more sophisticated approach was needed, and astronomers found exactly that. They decided to use the brightest objects in the entire universe, quasars, as cosmic spotlights. The core idea was simple: by directing light from a very distant quasar so that it passes through Andromeda's hypothesized halo on its way toward Earth, the gas within that halo should absorb some of that light at specific wavelengths. If they could detect these distinct absorption lines in the quasar's spectrum, it would confirm with certainty that the light had encountered a gas cloud belonging to Andromeda. By repeating this process with numerous quasars positioned strategically around Andromeda, they could essentially connect the dots and map the precise boundaries of its gaseous halo. So, what exactly are quasars, these cosmic beacons? Essentially, a quasar is the active core of an extremely distant galaxy. At the center of this galaxy resides a supermassive black hole vigorously consuming surrounding material, gas, dust, and even entire stars. Before falling into the black hole itself, this material spirals into what is known as an accretion disk. Friction within this disk heats the material to millions of degrees, causing it to glow with incredible brilliance. This glow is so intense that the light emanating from this small disk, which is only the size of our solar system, can outshine the combined light of every star in its host galaxy by hundreds of times. Quasars are the most luminous and most distant objects we can currently observe, lying billions of light-years away. This makes them ideal background sources of light for observation. Their light, traveling to us across billions of years, carries information about everything it encounters along the way, including the faint, wispy clouds of gas found in the halos of galaxies like Andromeda. Bringing this ambitious project to life required a highly specialized instrument, one capable of capturing ultraviolet light from distant quasars and resolving its spectrum with extraordinary precision. That instrument was the Cosmic Origins Spectrograph, or COS for short, installed aboard the Hubble Space Telescope. COS is one of the most sensitive spectrographs ever built. It specializes in the ultraviolet range because that is precisely where the fingerprints, the absorption lines, of various chemical elements are left. These elements, such as ionized silicon, carbon, and oxygen, are contained within the tenuous intergalactic and circumgalactic gas. This instrument allowed astronomers to peer directly into Andromeda's invisible atmosphere and for the first time measure its true physical extent. The project was named Project Omega, an acronym that stands for the absorption map of ionized gas in Andromeda. a team of astronomers led by Nicholas Lehner from the University of Notre Dame selected 43 quasars. These quasars were strategically positioned across the sky at various angles and distances from Andromeda's galactic center. Over several years, the Hubble Space Telescope systematically observed each of these quasars, utilizing the Cosmic Origin Spectrograph, or COS, to capture their ultraviolet spectra. What followed was the meticulous and painstaking work of analyzing this data. Scientists searched the spectra for subtle, dark lines, telltale signs that the quasar's light had been partially absorbed by gas. If these absorption lines were visible in the spectra of quasars that appeared close to Andromeda in the sky, but absent in those of more distant quasars, it would be direct proof that the gas belonged, specifically, to Andromeda's vast halo. This entire process was essentially a form of cosmic tomography. Instead of X-rays, the team used the light from distant quasars to scan and illuminate the galaxy's otherwise invisible structure. The results were nothing short of stunning. Scientists detected signs of a tenuous ionized gas permeating almost every direction around Andromeda, but the key finding was that they were able to pinpoint just how far this gas halo stretches. In certain directions, it reached distances of 2 million light-years from Andromeda's center. On average, however, its radius measured about 1.3 million light-years. This figure turned all previous understanding upside down. Let's put the numbers together. Our own Milky Way's halo has a radius of about 1 million light-years. Andromeda's halo has a radius of about 1.3 million light-years. The distance between the centers of the two galaxies is 2.5 million light-years. Simple arithmetic shows that 1 million plus 1.3 million is greater than 2.5 million. This means that the outer, most tenuous regions of these massive invisible halos are already overlapping. They are touching. The Milky Way and Andromeda are no longer completely isolated systems. First contact, the initial touch, has already taken place. So, what exactly is this contact zone? It's crucial to understand that this isn't some head-on smash between two solid objects. Instead, picture two massive clouds of fog or smoke slowly starting to blend at their edges. This is an area where the density of matter is incredibly low. We're talking maybe only a handful of atoms per cubic meter. You could fly right through this region in a spacecraft and not even realize it. But on the scale of entire galaxies, this means everything. This is the very beginning of the process where their vast gaseous atmospheres start to mingle. This means that atoms that were once firmly part of the Milky Way might now be floating within the halo of Andromeda, and the reverse is also true. This interaction has likely been underway for hundreds of millions, perhaps even billions of years already. We are currently living deep inside the merger zone. The eventual visible collision of the central galactic disks and the stars themselves is merely the final, most dramatic act of a cosmic play that has already begun. The core interaction, the one that will define all future galactic evolution, is happening right now in this invisible realm of rarefied gas and dark matter. This region, where the halos overlap, creating a shared atmosphere between the two galaxies, is essentially a unique cosmic laboratory. Astronomers call this environment the circumgalactic medium, or CGM for short. The CGM is thought to play a crucial role in a galaxy's life cycle because it acts as the primary reservoir of fuel for star formation. A galaxy can't sustain star formation indefinitely just from the gas within its disk. That gas eventually runs out. To keep the process going, the galaxy must constantly draw fresh gas from its external halo. This gas slowly cools, condenses, and rains down onto the galactic disk, igniting new generations of stars. Studying the exact zone where the CGMs of the Milky Way and Andromeda are mixing could provide invaluable data on this accretion process, specifically how gas moves and interacts in such extreme conditions. Ultimately, this knowledge helps us understand why some galaxies are still actively forming stars, while others have long since died and faded into mere clusters of old red stars. How will this intermingling of gas halos ultimately affect the future of both galaxies? It's difficult to say with certainty right now, but we can definitely hypothesize that the consequences will be intriguing. When two massive gaseous environments start to merge, we expect to see turbulence, shockwaves, and various instabilities emerge. This could accelerate the cooling of the gas, causing it to precipitate and fall onto the galactic disks. It's possible that even before the main collision, we might witness a significant spike in the star formation rate in the outer regions of both the Milky Way and Andromeda. On the flip side, this gravitational interaction could also powerfully stir up and heat the gas, temporarily putting the brakes on stellar production. Crucially, this mixing of matter means that future stars formed within our galaxy may contain atoms that originated in Andromeda, and vice versa. In a sense, the galaxies are already beginning to exchange the raw materials needed for their future generations of stars and planets. This effectively blurs the clear boundary between self and other at the galactic scale. So, what role does dark matter play in this whole process? It's the ultimate orchestrator. It was the gigantic dark matter halos that first initiated the gravitational interaction. Billions of years ago, their mutual attraction dictated the collision course of the galaxies, and it is their merging that forms the foundation of the entire process. Dark matter creates the gravitational potential, acting as a kind of invisible basin where ordinary matter, the gas, sloshes around and mixes. The dynamics of the dark matter determine precisely how the galaxies move, how they become distorted, and how they ultimately coalesce. When dark matter halos merge, they form a single, even more massive halo, the container within which the visible parts of the galaxies will dance and eventually unify. Modeling shows that the process of dark matter halo merging is smooth and far less dramatic than the collision of stellar disks. It is the slow, gradual unification of two invisible giants, a process that is already well underway. Are there other, perhaps more telling signs of this early interaction? Astronomers are actively hunting them down. For example, researchers are studying the most distant stars located on the very edges of the Milky Way and Andromeda, along with their associated satellite galaxies. If the dark matter halos are already engaging, their combined gravity might exert a subtle yet measurable influence on the orbits of these peripheral objects. It's possible that certain stellar streams on the outskirts of our own galaxy are already slightly warped or distorted by the gravitational pull of Andromeda's unseen halo. Astronomers are also searching for a so-called bridge of gas and stars, a faint filament that may have already stretched across the void between the two galaxies. So far, clear evidence of this sort remains elusive. This is hardly surprising, however, given how incredibly tenuous and nearly invisible the interstellar medium is across such vast distances. Nevertheless, as our telescopes and observational techniques continue to improve, we may soon be able to detect these subtle indications of an already ongoing galactic embrace. This finding forces a fundamental re-evaluation of the entire concept of a galactic collision. We used to imagine it as a single, discrete event, something scheduled for a specific point far in the future. But now we understand it's not an event at all. It is a long, drawn-out process, a process that actually begins long before the first stars ever interact. It starts with the gravitational interaction of the unseen halos of dark matter. Next comes the mixing phase, where their sparse, gaseous atmospheres begin to merge, a phase we are currently experiencing. And only then, billions of years down the line, do we reach the culmination, the dramatic fusion of the bright stellar disks. This completely alters our temporal perspective. We are no longer passive observers waiting for a distant future occurrence. We are already active participants. Our solar system, our planet, and even ourselves, we are all situated squarely inside this grand merger zone, this colossal cosmic melting pot where a new, unified galaxy is currently being forged. Let's take an even broader view of the situation. The Milky Way and Andromeda aren't the only players in this cosmic ballet. The local group also features a third major participant, the Triangulum Galaxy, or Messier 33. It is the third largest spiral galaxy in our group, and right now it's likely a satellite of Andromeda. Its ultimate fate is thus intricately linked to the destiny of the two giants. It's entirely possible that when the Milky Way and Andromeda merge, the Triangulum Galaxy will also be captured and ultimately absorbed by the resulting Milkomeda. Or perhaps it will be violently flung out into a distant orbit instead. Furthermore, dozens upon dozens of dwarf galaxies orbiting both the Milky Way and Andromeda will also be drawn into the process, much like bees swarming around two colliding beehives. Ultimately, tens of billions of years from now, the entire local group will likely coalesce into a single, supergiant elliptical galaxy that has successfully consumed all of its smaller neighbors. Yet, the story doesn't end there. Our local group is far from isolated. It is merely one component of an even grander structure, the Virgo supercluster. And the Virgo supercluster itself is just one part of Laniakea, a colossal supercluster of galaxies, one of the largest structures known in the universe. None of these structures are scattered chaotically, however. Instead, they organize themselves into what astronomers call the cosmic web. Picture a vast three-dimensional network where the threads or filaments are primarily composed of dark matter. Gas flows along these filaments feeding the galaxies, and it is at the intersections, the densest nodes of this web, where we find the massive clusters of galaxies. Galaxies are not isolated islands in the cosmos. They are bright, visible cities built along invisible, cosmic highways. Our eventual merger with Andromeda is therefore not just a local event. It is one small part of the global evolutionary process of the cosmic web, where smaller structures continuously merge over vast spans of time, creating increasingly massive entities. What kind of research prospects does this discovery unlock? The potential is enormous. First, we need to create a much more detailed map of this halo overlap zone. This will require observing even more quasars to get a three-dimensional picture of the gas's distribution, temperature, and chemical composition. The next generation of space and ground-based telescopes will be instrumental in achieving this. The James Webb Space Telescope, thanks to its unprecedented infrared sensitivity, will be able to study the coldest and dimmest components of this environment. It will also be able to observe the most distant stars at the periphery of galaxies, whose movements might reveal the gravitational influence of a neighboring halo. Future giant ground-based observatories, such as the extremely large telescope, will be capable of obtaining even more detailed spectra, which will, in turn, inform us about the dynamics of this gas. We can also study other galaxy mergers to gain a better understanding of our own specific situation. The universe is full of such examples at every stage of the process. Take, for example, the famous antennae galaxies, a pair that is currently in the thick of a collision. They exhibit long tidal tails and regions of intense, furious star formation, all the signs that the Milky Way and Andromeda will share in the future. By observing systems like these, we can test and refine our computer models of mergers. Furthermore, by studying galaxy pairs currently at the same close approach stage as the Milky Way and Andromeda, we can attempt to find evidence of their interacting halos. This would confirm that our discovery is not an exception, but rather a fundamental general rule in galaxy evolution. Ultimately, billions of years from now, once the final stage of the merger is complete, the local group will have consolidated into a single, colossal, elliptical galaxy. This new entity will no longer feature the beautiful spiral arms or the active star formation we see today. Instead, it will be a vast spheroidal cluster, a celestial graveyard of trillions of old red stars whirling in chaotic orbits around a single central nucleus, where the supermassive black holes of the Milky Way and Andromeda have finally coalesced. Our own sun will have long since faded into a white dwarf. But if an observer could somehow view the night sky from within this future galaxy, they would witness a radically different panorama. Instead of the familiar bright swath of the Milky Way stretching across the heavens, the sky would be more uniformly filled with stars, and critically, it would be much, much lonelier. Due to the universe's accelerating expansion, virtually all other galaxies will have rushed far beyond our visible horizon. Our newly unified galaxy will be left entirely alone, a single island of light in a dark, empty, and increasingly isolated cosmos. So what does all this truly mean for us, right here, right now? At first glance, this knowledge doesn't change anything about our everyday lives, but on a profound philosophical level, it changes absolutely everything. It reveals that the universe is not a static backdrop, but a living, breathing, constantly evolving organism. The forces shaping its appearance take billions of years to unfold, yet they are relentless and continuous. The realization that we are already a part of this grand cosmic merging structure dissolves all boundaries. Our home is not simply planet Earth, nor the solar system, and not even just the Milky Way galaxy. Our home is this immense, unified structure, slowly being born right before our eyes. We are connected to Andromeda not only by a shared future, but also by a common present. The atoms in our very bodies may one day be incorporated into new stars, lighting up in a different, currently distant galaxy. It is a profound reminder of our deep unity with the cosmos and the incredible mysteries it still keeps hidden. So, let's take a moment to summarize our quiet journey. We began with the well-known fact: in about 4.5 billion years, the Milky Way and Andromeda are set to collide, but then we looked deeper, beyond visible light, into the realm of dark matter and diffuse gas. And we discovered that galaxies aren't merely stellar disks. They are gigantic, invisible spheres, halos that stretch for millions of light years. The most striking discovery is this: these halos, the true boundaries of our galaxies, are already in contact. The collision is not an event reserved for the future. It is a process that is already underway. You and I are living right in the thick of this cosmic merger, in the zone of first contact. This realization is simultaneously mesmerizing and makes us feel like a part of something truly immense and grand. Thank you for spending this time with me, exploring the unseen corners of our universe. I hope this journey was both peaceful and insightful. If you enjoyed this discussion, please hit the like button and subscribe to the channel so you don't miss future cosmic stories. Now, before you fully drift off to sleep, I want to leave you with a final thought. What other incredible secrets do you believe the invisible realm of dark matter is hiding from us? Share your wildest ideas in the comments below. Good night and sweet dreams.